Hello students, welcome to another video. Today we are going to start the last chapter of number theory, that is some Diophantine equations. Some Diophantine equations. Some Diophantine equations. So first of all, we will take the definition of Diophantine equation. Definition of Diophantine equation. Definition of Diophantine equation. The equation of the form ax plus by is equals to c is called Diophantine equation or a linear equation. A linear equation in two variables. The linear equation in two variables having integral coefficients. That is, the coefficient of the numbers x and y must be integer with having integral coefficients. So that is the equation of the form ax plus by is equals to c. So this is equation in variable x and y with coefficients a, b and c, where this a, b, c are integral, that is a, b, c are integers. A, b, c are integers. So these equations are called Diophantine equations. The linear equation in two variables having integral coefficients, that is the equation of this form, are called Diophantine equations. That is, we have to find the solution. If we have to find the solution of this equation, we have to find the values of a, b and c. That values of, here x and y are variables, so solution must be values of x and y. So we have to find the solution of this equation. So we have to find the value of x and y such that x and y satisfies these values. So a, b, c are coefficients. That is, if you have given 3x plus 2y is equals to suppose 9, then we have to find the values of x and y, and that value must satisfy our equation. So in this chapter we will find the solution as integers. So instead of rational numbers and real numbers, we will find just integers. We are going to just focus on the integral solutions, that is, the solution must be in integers. So first of all, we will take one remark. This is just a recall from the second chapter, that was one theorem, the congruence ax is congruent to b mod m. Ax is congruent to b mod m as solution. We know that this congruence as solution if and only if, this was our theorem, if and only if the GCD of a and m divides b. If and only if, suppose this g divides b and this g is GCD of a and m, and g is GCD of this a comma m. G is GCD of a m, and the solutions of this congruence forms an arithmetic progression. With common difference this m by g. With common difference m by g. This is the theorem of second chapter. So this theorem is useful to solve the next theorem, to prove the next theorem. So first of all, we will take one theorem of this Diophantine equations. The Diophantine equation means the equation of the form ax plus by is equals to c. For that, a, b, c are must be integers. So that is the equations of the form ax plus by is equals to c, where these coefficients a, b, c are integers. Those equations are called Diophantine equations. So next theorem will give us the idea whenever this equation has solution or whenever this equation has no solution. Next theorem, statement of the theorem is let A, B and C, A, B and C are integers. This is the important theorem for the as far as the university examination concerned. A, B, C are integers with not both A and B 0, not both A and B equals to 0, not both A and B equals to 0, that is A and B are non-zero, not both A and B is equals to 0. Let G is greatest common divisor of A and B. G is GCD of AB. Now, if this GCD doesn't divide C, G doesn't divide C, then the equation AX plus BY is equals to C, that is the Diophantine equation, has no solution. Up to this statement gives us, if we have given some Diophantine equation, suppose some number integer into x plus some integer into y is equals to some another integer, then if you have asked to find the solution, then you have to first of all find the GCD of these two numbers, and if the GCD divides this number, then we will see that this Diophantine equation has solution. If that number GCD of these two numbers doesn't divide this number, then we will say that this equation has no solution. So if G is GCD of A and B and G doesn't divide C, then this equation AX plus BY is equals to C has no solution. If this G divides C, then the equation AX plus BY is equals to C has, then that equation has infinitely many solutions. That is, there are infinitely many pairs of x and y which satisfy this equation. Infinitely many solutions, and the pair x1 y1 is one integral solution, that is its first solution, one integral solution. Then the other solutions are of the form. X is equals to x1 plus kb upon g, and y is equals to y1 minus ka upon g. So this is the statement of the theorem. So this theorem says that A, B, C are integers with not both A and B is equals to 0. Let G is GCD of AB, that is G is GCD of these two numbers AB. And if this GCD of A and B divides C, then this equation has infinitely many solutions, and GCD of A and B doesn't divide C, then this equation has no solution. Our GCD of A and B doesn't divide C, then this Diophantine equation has no solution, and our GCD of A and B divides C, then this equation, that is the Diophantine equation, has infinitely many solutions. And suppose this is the first solution, then the other solutions are of the form x is equals to x1 plus kb upon g, and y is equals to y1 minus ka upon g. So in this, to prove this result, we have given that A, B, C are integers and A and B are non-zero. Also we have given that G is GCD of A and B, and if our G doesn't divide C, then we have to prove that this equation has no solution. And after that, if our G divides C, then we have to prove that this equation AX plus BY is equals to C has infinitely many solutions. And after that, if x1 and y1 is one pair, then the other solutions are of the form this. So we have to prove that. First of all, we have to prove if G doesn't divide C, then we have to prove this equation has no solution. Secondly, if this G divides C, then we have to prove that this equation has infinitely many solutions. And after that, if this x1 y1 is one pair, that is the first pair, then we have to prove that this x plus then other solutions are of this form. So to prove this result, this theorem may be asked in the university examination. If the examination is offline, then this question may be asked for 5 marks. So to prove this result, we need the first remark, that is we must know that Ax is congruent to B mod M as solution if and only if GCD of A and M divides B. So first of all we will write the given things. Here we have given that A, B, C integers. Let this A, B and C be integers. Also we have given that A and B both non-zero and G is GCD of GCD of A and B. Now this is just given thing. First of all we will suppose G doesn't divide C and we will prove this equation has no solution. Suppose G doesn't divide C. Now we have to prove that this equation Ax plus By is equals to C has no solution. We can just rearrange this equation as Ax, so minus C is equals to minus of By. Ax minus C is equals to minus By, and just rewriting this as B into minus of Y, we will say that Ax minus C. So this, after using definition of divisibility, we can say that this B divides Ax minus C. This will give B divides Ax minus C by definition of divisibility, and we can write by using definition of congruence it as this Ax is congruent to C mod B. Ax is congruent to C under modulo B. Just rewriting this equation in this form, and now we know that this congruence has solution if and only if GCD of this number and this number, that is A and B, divide C. But here this G is GCD of A and B, G is GCD of A and B, and that G doesn't divide C, so that this congruence has no solution. Now means our first claim is proved. Therefore it has solution. This congruence has solution if and only if our G divides C. Hence which is contradiction, that is this will give, but our G doesn't divide C. This implies G doesn't divide C. This implies this equation Ax plus By is equals to C has no solution. In the first, here we have suppose G doesn't divide C, and we have to prove this equation has no solution. We just rearrange this equation in the form of congruence, and we know that this congruence has solution if GCD of A and B divides C, but our G is GCD of A and B which doesn't divide C. This means that this congruence has no solution, that is this Diophantine equation has no solution. Now secondly, we will suppose G divides C. Suppose G divides C. Now our theorem says that if G divides C, then this equation, that is this Diophantine equation, has infinitely many solutions. Now to prove that this equation has infinitely many solutions, here we have given that G is GCD of A and B, and here our G divides C. So as G is GCD of A and B, we can use the result of expression of GCD into linear combinations. We can write there exists some x naught y naught belongs to z, that is x naught y naught be in integers, such that G can be written as linear combination of A and B, that is Ax naught plus By naught is equals to G. Now after dividing throughout by G, we can write it as Ax naught by G plus By naught by G is equals to 1. Here we are dividing the both sides by G, since G by G is 1, which is itself integer, and G is GCD of A and B. So G is first of all common divisor of A and B, that is G divides A and G divides B. So this division will give integer solution, some integer. So this must be an integral solution. So Ax naught upon G plus By naught upon G, but we are willing to prove the Diophantine equation Ax plus By is equals to C has infinitely many solutions. So we need this equation A into some x plus B into some integer is equals to C. So after multiplying both sides by C, we can write, multiplying both sides by C, we can write A C x naught upon G plus b cy naught upon g is equals to c. That is, you can write a this cx naught upon g plus b into cy naught upon g is equals to c. So this is again of the form a into some x plus b into some y is equals to c. So this cx naught by g and cy naught by g is integral solution of this equation. This is integral solution since our g divides c. G divides c. So this division will again our integer since g divides c. So if we write suppose 10x naught upon 5. So 5 divides 10. So that will our integer since our g divides c. So this is again integral solution. So this will give x naught y naught are just belongs to integer, that is are some integer. So for any x naught y naught we will get some different solutions. Therefore we get cx naught by g and cy naught by g is solution of ax plus by is equals to c. Hence we get, if our g divides c, then we will get this Diophantine equation has solution, and this Diophantine equation has infinitely many solutions since this x naught y naught are in integers. Now we will prove the if x1 y1 is one solution, then other solutions are of this form. To prove this result, we will take x1 y1 is one solution, and suppose x and y are is some another solution, then x and y are of this form. So let xy and suppose x1 y1 are the solutions of ax plus by is equals to c. That is are the solutions of some Diophantine equation. Therefore these are solutions means this satisfies the Diophantine equation, that is this pair satisfies the Diophantine equation, that is ax plus by is equals to c, and again this pair satisfies, that is ax1 plus by1 is equals to again c. Suppose this is equation number 1, this is equation number 2. Now subtracting this equation number 2 from equation number 1, therefore by 1 minus 2, that is subtracting equation number 2 from equation number 1, we will get, just subtracting means, so a is common, x minus x1, again is b is common, y minus y1, c minus c is 0. We will get a x minus x1 plus b times y minus y1 is equals to 0. X minus x1, a into x minus x1 plus b into y minus y1 is equals to 0. So we can rearrange this as a into this x minus x1 is equals to this minus of b and minus of b y minus y1. So just absorbing the minus sign, we can write this y1 minus y. Multiplying by minus sign, we get minus y plus y1. So just writing y1 minus y, right hand side as it is. A into x minus x1. We have to prove that x is of the form some x1 plus kb by g, and y is of the form y1 plus k by g. Now here we get a times x minus x1 plus b times y1 minus y. Now if we divide both sides by g, that is GCD of a and b, we get, dividing both sides by g, we get a upon g times x minus x1 is equals to b upon g y1 minus y. This is suppose equation number some star. Now by using, we are going to use the definition of divisibility on both the sides, because a by g into some integer is equals to this term, and again here b by g into some integer is equals to this whole term. So by using definition of divisibility, we can say that this a by g divides b by g into y1 minus y. Therefore by definition of divisibility, we can write a upon g divides b upon g times y1 minus y by definition of divisibility, by using definition of divisibility. Now as GCD of a and b is equals to g, so a GCD of a upon g and b upon g will become 1, as as G is GCD of A and B. Therefore, if you divide whole term by G, that is GCD of A upon G and B upon G will become 1. Therefore, if GCD of these two terms is 1, that is GCD of A upon G and B upon G is equals to 1, then we have the result. If A divides BC and GCD of A and B is equals to 1, then this A divides C. So using that result, we can write A upon G divides Y1 minus Y. Using this result, we can write A upon G divides Y1 minus Y. This is my result. If A divides B into C and GCD of AB is equals to 1, then A divides C, that is GCD of these two numbers is equals to 1, then our A divides C. Using this result, we have this. So just rearranging this or using definition of divisibility, we can write Y1 minus Y, that is Y1 minus Y is equals to A by G times some integer, A upon G into some K, where K is an integer. Now just simplifying this or rearranging this, we get A minus Y is equals to AK by G. This Y1 goes on this side, so become minus 1. So this will give Y is equals to Y1 minus AK upon G. This is the first value of Y. Again in the same equation, that is from equation using definition of divisibility on equation number star, we can write B upon G divide this whole term. Again GCD of AB is equals to 1, so A by G and B by G, GCD of A upon G and B upon G will become 1. So our B upon G divide this term and we will get our required value of X. Again using equation number star, we can write B upon G divides A upon G into X minus X1. B upon G. Again GCD of A upon G and B upon G is equals to 1, as we have seen earlier. This we can write this B upon G divides X minus X1. Reason behind this, since GCD of A and G with B by G is equals to 1. This is the reason, since GCD of A by G with B by G is equals to 1. So this, by using definition of divisibility, we can write this X minus X1 is equals to B into some integer K upon G. B into some integer K upon G, where K is again an integer. So just rearranging this, we will get X is equals to X1 plus BK upon G. Therefore, for all the solutions of Ax plus By is equals to C, we have X is of the form this and Y is again of this form. Here using definition of divisibility, we are using the integer, that is the notation K here. Again the same notation K here. You don't need to write the notations K1 and K2, because if you take these notations K1 and K2, then you will get the contradiction to the equation number star. So this notation that K must be same. So you will get X and Y. Therefore we can write thus all other solutions, that is solutions other than x1 y1, other solutions of Ax plus By is equals to C are of the form X is equals to x1 plus Bk upon G and Y is equals to this y1 minus ak upon G. Hence the proof of this theorem.